AP Chemistry, and welcome to Entropy, right? And now we're going to actually talk about what entropy means at the particulate level, right? At the particulate level, entropy really is a matter of probability, right? What is the most probable arrangement, okay? Or which arrangement has the greatest probability, I guess would be another way to look at it. Which arrangement has the greatest probability? So here, let's say that we have two particles, A and B, or red and blue, trapped in one side of a system, right? And we open this up, which means that they're going to spread out. We know that they're gaseous, and we know that they will spread out on their own, right? And we said that we seem to understand, right, that this arrangement is not likely, right? With two particles, it's a little bit likely. All right, and if we look here, right, going back to probability, if any of you guys are in AP Stat, then maybe you would have already talked about this. And I do believe you would have talked about this basic stuff in Algebra 2. So anyway, if we look here, right, there is a 1 in 2 likelihood that this red one is in this container, okay? There's a 1 in 2 likelihood that the blue one is in this container, right? Which means that the probability of them being in that container together is 1 over 2 squared, right? 1/2 times 1/2. And that gives us our probability of 1/4 that both ones happen to be in this container by themselves, okay? Which means that there is a 1 in 4 possibility that they're both in this container by themselves. Yes? Okay. All right. Moving along. If we wanted to see if there were 3 particles, now we would say that our probability was 1/2 raised to the 3rd power, right? Which gives us what? Right, a 1/8 probability, so 1 out of 8 probability that they're all in one container. Now, if we were to talk about the options of a mole, 61022 times 10 to the 23rd particles, all being the same container, right? That is vanishingly small, almost 0. Yeah, does that make sense? Right? Meaning the probability of an entire mole of particles being in one container is almost 0, right? And so microscopically, there's almost no chance that they're all in one container, which then makes sense because macroscopically, we understand that no, they're not all going to be in one container. They're going to spread themselves out and take up all the space allotted to them, okay? So, right, probability is part of what entropy is, right? What is the most probable arrangement of my particles, okay? So then that brings us to terminology here. Microstates, not to be confused with state, right? So we're not just talking about states, where states are our phases, solid, liquid, gas, and aqueous. Microstates, meaning microscopic arrangements of my particles, okay? Boltzmann equation, right? Boltzmann is the name of the person that is credited with this equation, right? Has this equation wherein we say that entropy, this is entropy, this is the number of microstates. K is this constant that he came up with, right? Which says that obviously as the number of microstates increases, our entropy increases. Meaning if there are more ways microscopically for my particles to be arranged, then my particles have more entropy, okay? Which by therefore means that more entropy means more microstates, more possible arrangements for my particle, okay? And this, key takeaway, more microstates, more entropy. Okay, so let's go ahead and add some better ways to describe entropy, because obviously we're not going to sit around and calculate probabilities for all sorts of things, and some things don't have probabilities in terms of how to describe them, right? So one of the easiest ways to describe microstates is via motion. What kind of motion can my molecule or particle do? Okay, so we have translational motion. This is the easiest one to discuss. Translational motion is the physical movement of my particle. So from point A to some other point, right? From here over here. So it is the physical movement of a particle across space. Okay? Rotational motion, like it indicates here, right, means about a fixed axis, my molecule or particle is able to rotate about that fixed axis. Okay? Here, if we look here, one kind of vibrational motion, right, is the shortening and lengthening of these bonds, right? It is the squeezing and the expanding of that bond angle, which we talked a little bit about last year, and we'll talk a lot more about this year. And over here, right, it also refers to again, the back and forth motion, right? And again, all right, so microstates, one kind of microstate has to do with just motion. Now, phases go hand in hand with our microstates also, but they also go hand in hand with what we just talked about for motion, right? increasing entropy as we go from solid to liquid to gas, which should make sense, right? Gas has far more microstates because we have translational motion, right? As in my particles can literally move across the space allotted to them, right? Translational motion, obviously they can vibrate because anything that has bonds can vibrate, and it can rotate because they are free in space, okay? If we go to liquid water, there is some translational motion, not as much as with a gas, but they also can vibrate and they can rotate. If we look here, we have a rigid crystalline structure. We can vibrate only, yes, because the whole point of a solid is that one particle is fixed in relation to its neighbor, which means that we only get this kind of motion, right? The motion that happens, in their chemical bonds, all right? The kind of motion that happens in the chemical bonds themselves, okay? So very, very important stuff. So what that means is the less ordered my phase, the greater my entropy, okay? Next up, this is a graphical representation of the last figure, wherein here we have temperature, here we have entropy. As we increase temperature, what do we notice happens to my phase? Ding, ding, ding. Right, we go from solid, liquid to gas, meaning that these right here obviously represent what? Right, this is our melting point, and this is our boiling point, right? And why do we see this? Right, because as we change phase, that's where we get the greatest increase in our entropy, right? Upon going from solid to a liquid, we introduce boatloads of motion, right? We reintroduce translational and rotational motion. Here, we get an even bigger increase because now my particles are no longer confined to be adjacent to their neighbors, okay? And that, again, going back to what it means to be a gas, right, in kinetic molecular theory, they have no attractions to their neighbors, which is why that increase in entropy is so much more significant. Okay, in terms of my atoms, right, we just said that there is a level of entropy involved with bonds, right, meaning that this bond, these two atoms can move closer and further, right, these two atoms can move closer and further, so forth and so on, right, which means that as the complexity of my molecule increases, we also increase in entropy, yes? Right? As the complexity of my molecule increases, meaning I have more atoms and more bonds, I also increase in entropy. Okay, so all of this to say, right, that again, if we think back, right, increasing entropy is a favorable process, right? Increasing the entropy of the universe means that my process will be spontaneous. Entropy meaning number of microstates. Increasing number of microstates means increasing entropy, which is a thermodynamically favorable concept, okay? Energetically favorable, all right? We're going to pause here and we'll pick up in the next one, adding some quantifiable information to our entropy. All right, thanks for listening. Be good, and I'll see you soon. Bye.